Welcome to today's Explainer. Let's jump right in, because today we are tracking the incredible hero's journey of data. You know the kind, messy, flat, legacy data that's been gathering digital dust on a hard drive for a decade. We're going to look at exactly how it transforms into a modern, totally private, AI-powered interactive graph application. It's a seriously fascinating technical evolution, and we are going to break down the exact tech stack that makes the magic happen.
But before we get into the nuts and bolts of the architecture, I want you to picture a digital folder. You probably have one just like it. It's stuffed with thousands of duplicate family photos, broken file links, overlapping text files, and metadata that is just a complete disaster. Ask yourself, how do you even begin to sort that out? It's the ultimate digital junk drawer. Just looking at it gives you a headache, right? Well, today we are unpacking a highly engineered solution to that exact problem.
Okay, here is the architectural blueprint for the day. We'll start by taming the data vault, then map out the ultimate tech stack, dive into visualizing interactive data trees, and finally, check out the AI Asset Management Hub.
All right, part 1, taming the data vault, cleaning up the chaos.
Every great data project starts by cleaning up the mess. In this case study, that means resolving a massive amount of duplicated media. Imagine overlapping folders, like these Atkinson Media ones, that have just mirrored themselves over the years. Now, nobody wants to manually click through thousands of images, so an automated parser utility steps in. It generates a SHA-256 cryptographic hash for every single file. If the hashes match perfectly, boom, we know the files are identical at the byte level. This lets the system confidently delete the copies, like that Charles Ryder census duplicate, while permanently protecting the master record. It's a total lifesaver.
And the results? Once the vault is deduplicated, the database is lean and optimized. No more bloat. Now the AI matching engine can actually get to work. It scans high-value, unlinked media sitting in a temp folder. Take this unindexed photo of Thomas Lafayette Ryder's grave, for instance. The AI evaluates the file path, the base name, the metadata, and suggests mapping it to the correct verified profile with a massive 98% confidence score. Just like that, we've gone from a chaotic junk drawer to a highly verified, actionable dataset.
Moving on to part 2, the ultimate tech stack. Let's look at this production-grade engine.
The crucial thing to grasp here is the exact data pipeline. It all starts with a flat text file, specifically a GEDCOM file, which is pretty much the gold standard format for legacy family tree software. From there, that data flows directly into a Node.js or Python parser. The parser rips out the metadata and structures it relationally inside a PostgreSQL database. Then, a modern Next.js backend API serves that structured data right to a React Flow frontend, drawing it dynamically on your screen. It is such a clean, logical, and highly effective architecture.
But to make this pipeline lightning fast and AI ready, your specific tech choices really matter. The bedrock here is Postgres 16. Now you might ask, why not something lightweight like SQLite? Well, tracing deep, multi-generational bloodlines requires advanced relational constraints and recursive queries. Plus, we're equipping Postgres with the PG Vector extension. This is a total game changer because it lets us house standard relational data, like names and dates, right alongside complex AI data arrays. Tie it all together with Next.js 14 and the app router to handle the APIs, and that deep relational data gets passed seamlessly to the UI.
All right, part 3, visualizing interactive data trees. Let's see how this plays out on the front end.
Because we definitely don't want a static, boring chart here. We want rich interactivity. Our Next.js API routes take those raw database rows and transform them into a strict JSON format made up of nodes and edges. Basically, a node is a person and an edge is the relationship connecting them. In computer science, this creates what's known as a directed acyclic graph, or DAG. That just means the data flows in one single direction, generation by generation, without creating impossible circular time loops. It essentially turns your data into a massive, interactive digital detective board.
To actually draw this DAG on the screen, we're using a library called React Flow. But here is a massive catch, and it perfectly illustrates why architectural choices matter so much. Standard React Flow forces you to manually assign an X and Y coordinate to every single node. Imagine the absolute nightmare of manually plotting pixel coordinates for 500 great-grandparents. You would end up with a tangled, overlapping disaster. To fix this, the stack integrates ELK's certified layouts, specifically ELK.js. It's a professional-grade auto-layout algorithm built exactly for DAGs. It dynamically spaces out those complex family generations so they literally never visually overlap.
Finally, part 4, the AI Asset Management Hub. This is where we bring in local, private intelligence.
Okay, so we've got these gorgeous nodes on our screen, styled out in a sleek, dark Cyber Obsidian Tailwind CSS glass morphism theme. But how do we actually let a user interact with all the biographical notes and media dynamically? And crucially, how do we do it without sending deeply personal family histories to some public cloud server and completely compromising privacy?
The secret sauce is building a local retrieval augmented generation, or RAG, system. The execution runtime is handled by Ollama, meaning you run these powerful AI models entirely on your own local hardware. That means no OpenAI tokens and zero data leaving your machine. For the actual search capabilities, the stack relies on an embedding model like BGE large-en, which is blisteringly fast running locally to create vectors from your notes. And orchestration tools like LangChain chunk up those long historical biographies so the AI can actually read them efficiently. Your sensitive family records stay locked down on your private infrastructure. When you integrate this AI stack with the UI, magic happens. Hovering or clicking on a family member's node triggers a high-tech media inspector overlay. This panel instantly pings the database and surfaces those specific, deduplicated, high-value images we saved way back in step 1. It gives you clean metadata, semantic tags, and links everything back to the exact right person flawlessly.
But we can take it one step further. Because this AI is local and context-aware, the overlay includes an interactive prompt area. This is the ultimate victory of this whole architecture. It turns a flat text file into a brilliant interactive co-writer. You can literally ask the app to draft compelling historical narratives on the fly, summarize migration patterns from the 1800s, or generate rich biographical stories based on the fragmented notes attached to that specific note. It is just insanely powerful.
It truly is a masterclass in taking flat, messy legacy data and engineering it into a secure, modern, highly interactive app. So as we wrap up this explainer, I want you to think about your own archived files. What hidden histories are locked away in your digital junk drawer? And what incredible stories could you finally uncover if you gave that data the engine it actually deserves?